So this is our second part for linear regression. We're going to start off with just a few notes about our correlation and regression. So the first thing is working variables. Okay. So we've interpreted our slope, B1, oh, sorry, that's coming all from another class. In our class we write it beta 1. Okay. Hat. Okay. So we'll interpret our slope to be the change in our predicted value of y. Sorry, the change in our predicted value of y associated with a 1 unit increase in x. Okay. However, we cannot show, and this is the biggest thing that I have to drill into, we cannot show that a change in our x value causes a change in our y value. Okay. Really, regression can only show us, okay, that two variables move together and that the explanatory variable contributes information for predicting the dependent variable. Okay, we often call this association versus causation, if you've heard that phrase before. So, like for instance, as mattress sales have increased in the past, college professor salaries have also increased. Okay. Does this show us that professor salaries depend on mattress prices? Okay. No. So if you guys go out and buy a little more expensive mattresses, do I get paid more? No. Okay. What's happening here? We just have our inflation, right? And so both mattress prices and professor salaries are affected by inflation. And so we have that third variable, our inflation, our long-run growth in the national economy. That sounds better. And it's our lurking variable. So you often have these lurking variables, which are variables you weren't accounting for, but still affect your results. Okay. So you just have to be careful to remember that, okay, they move together. That means mattress sales prices might help me predict professor salaries, but they're not actually causing a change. Okay. So as one note, the other note is about outliers and influential observations. Okay. So linear regression is very sensitive to outliers. If an observation has a strong influence on the regression line, we call it an influential point. Okay. So, for example, watch what happens to the line if I add an extra point. So we start with this data set. Here's my line. Seems to fit it pretty well. You can see the actual equation of the line. Okay. And our squared value is 0.748, so we can explain about 75% of our variation in our y values by our line. That's not great, but that's fairly good. I can probably make fairly good predictions. Okay, notice what happens when I add in this point. What happened to the line? Our R-squared value went way down. Okay, the slope changed a lot. Okay, at least visually it changed a lot, but it went down about 4 if you look at the equation on the line. And also what happened to my intercept? My intercept jumped from 113 to 332. Okay, so 1 point threw off my line completely. Okay, but that wasn't actually too bad. Notice what happens when I add in this point. Okay, does my line even seem to fit my data anymore? Okay. No, it's not even going through most of those points. Notice my R-squared value is all the way down to 0.07. That's horrible. Okay, and I mean, at that point you may as well just randomly guess. It's probably going to tell you about as much as your line does. Okay, and my slope is all the way down to about 5, and my intercept is all the way up to over 1,000. Okay, so again, just keep in mind one outlier can completely throw off your results. Now, we did talk about dealing with outliers in these classes before. We said you can remove the outlier if you're sure it was a mistake. But if it is naturally occurring, you don't want to take it out of your data set because it is contributing important information. Okay, so those are just some PSI notes. Now we're going to start section 12.3, which is inference for linear regression. Okay. So we looked at our sample data and we found our regression line as such. Okay. However, just like in our previous chapters, there's a difference between our sample statistics and our population parameters. So we can think of having a model that's the best fit for our population, which we said before we did y equals beta naught plus beta 1x. Okay. So there's an unknown population slope, there's the unknown population intercept, Now, we've also talked briefly yesterday about correlation. So we have population correlation, which we use the symbol rho. And we estimate it with our sample correlation R. Okay. We have our unknown population variance of the errors, sigma squared, that we estimate with our mean square error, sigma hat squared. Okay. And also, just when we go through and look at our output on the computer output, lots of times sigma hat, so just the square root of it, is called the standard error of the model. So if you're ever looking at linear regression output and they tell you the standard error, that's probably our sigma hat. So, just like before when we had sample means and population means, and we did a test to see what the population mean might be, and we did confidence intervals to see what the population mean might be, we're going to do the exact same thing here, but we're going to do confidence intervals for our slope instead. Okay. Why do you think I'm going to want to do a confidence interval for my slope instead of a confidence interval for, say, my y-intercept?
Y-intercept.
Okay. Well, and remember, we said that our y-intercept doesn't always have a practical interpretation. So lots of times I don't really care about the y-intercept. I just want it there to fit my line the best I can. So there are actually formulas to find constant intervals for y-intercepts. There's even formulas to find constant intervals for your correlation. And even though I've never used one, I'm sure there's a constant interval out there for your standard error. Okay, or your mean square. So there's confidence intervals that we can find for everything, but we're going to use the confidence interval for the slope because that's usually what we care about the most. Okay. Now remember, our form for confidence intervals, our general form, is always the estimate plus or minus a critical value times the standard error of the estimate. Okay, which means that our confidence interval for our slope, our true population slope, beta 1, is, sorry, I keep bringing over notation from the wrong class. Beta 1 hat plus or minus our critical point times the standard error for beta 1 hat. Okay, so again, it's just our estimate plus or minus our critical point times the standard error for our estimate. Okay. Now notice here, this is important though. T star is the critical value from the T curve with n minus 2 degrees of freedom. Okay. Slightly different than when we used it for inferences on our mean. So to try an example, a study was conducted to see if fidgeting or non-exercise activity could help reduce fat gain. Here are the results. Okay. Notice there's a lot of stuff on here. Okay. There's n. N is my sample size. Okay. There's r squared, 0.6. Not great. We can only explain about 60% of our variation with our y values. The rest comes from natural variation from person to person. Okay, r, that is my correlation. Okay, and standard error. So I told you, I'm going to put this on there, is most softwares don't tell you mean square error. They write it as standard error. Okay, and you need to be able to recognize it so when you're like, ask you what the mean square error is, you can find it. So standard error is 0.74 is our sigma hat. So that's the standard error of our overall model, sigma hat. So if you want to find the mean square error, you would have to square that number. Okay. Also, notice this depth.var, that's short for a dependent variable. So that tells us that our fat gain is our actual variable that we're predicting, our y variable. Then coming down here to our regression output, you have intercept, will always just be labeled intercept, so that's for your y-intercept. And then your explanatory variable is, in this case, our NEA, so non-exercise activity. Okay. You have your coefficients. So basically, that means that our estimate for our intercept is 3.5051. And our estimate for our slope is -0.0034. So that's how you read that part of the table. Okay. Notice each one has its own standard error. So you have your overall standard error for the model, then you have standard error for the intercept, and you have standard error for your x values. Okay. And then we have t-values and p-values, which we'll use later. And it will even give you a 95% confidence interval for both your y-intercept and your slope. So we're going to learn how to do it by hand, just for fun, or if you want something besides a 95% confidence interval. Or if you wanted, say, a one-sided confidence interval. Okay, so what is our equation for the linear regression line? You just have to pull everything off the chart. So my intercept is 3.5051 plus my slope, so I guess minus 0.0034x. So that's my estimate for my model or the equation for my regression line. Let's see, so what is your estimate for beta naught? I guess we already wrote that at 3.5051. And what is your estimate for beta 1? Negative 0.0034. So what does that mean? That means the more your NEA goes up, so the more and more you fidget, okay, then your fat should go down. Okay, so that was just reading the table, and then I put the table again on the next page, so we can do some more with it. So what is your estimate for the variance of the errors? So they are asking for sigma hat squared, but we only know sigma hat. So we know that the standard error for the model is 0.740. So if I want the estimate for the variance of the errors, I have to square that. Next, find a 95% confidence interval for the slope, beta 1, and interpret it. So first of all, I'm looking for a 0.95% confidence interval, which means that I have 0.025 in each tail. Am I using the Z or T table? T. So I'm going to use the T, and I need my degrees of freedom, which are n minus 2. Okay, so I know it's different, but you can use that. So degrees of freedom is n minus 2. So 16 minus 2 gives me 14 degrees of freedom. Now, do you see 14 degrees of freedom anywhere on your output, on the computer output? You might notice that right here, it even tells us that degrees of freedom are 14. But let's go to our T table. We want 14 degrees of freedom and 0.025A in the right tail puts me at a critical value of 2.145. So we have that our critical value is 2.145. Now the equation for our confidence interval is our estimate plus or minus our critical value times the standard error for our estimate. Okay, so looking at the output, the estimate for my slope. Estimate for my slope is negative 0.0034 plus or minus my critical value, 2.145, times the standard error for the slope. Now again, notice there are 3 different standard errors on your output. Which one do I want here? Okay, so because we're dealing with the slope Here's for the NEA, so if my estimate is negative 0.0034, the standard error of that estimate is the number next to it. So standard error is 0.0007. So I got negative 0.0049 to negative 0.0019. Notice that does match the results given in the computer output, just accounting for rounding. And how did you interpret this? Okay, so we can say something like we're 95% confident that our population slope, so if we had all the data and not just the sample, that the slope of that would be somewhere between negative 0.0049 and negative 0.0019. So you could do it like that, or you can interpret it just a little bit more and give your boss just a little more information by telling him, well, what does slope actually mean? So kind of putting your confidence interval interpretation and the definition of slope together. So that would look something like, we are 95% confident that if the non-exercise activity increases by 1 unit, that will, is that going to go up or down? Okay, so we have negative slope, so if that will decrease, between 0.0049 and 0.0019 units. So just putting our definition or interpretation of confidence intervals and definition for slope together to give them a more meaningful interpretation. That's how you find a confidence interval. Any questions? Okay. Once you found one confidence interval, you should be able to find any confidence interval for anything. Okay. So let's switch gears just a little bit, okay, and read into our next topic. So should there be a linear relationship between the amount of candy you eat and the grade you get in this class? Okay. Should the amount of candy you eat affect your grade? Okay, you're saying yes. For the most part, I mean, unless you're eating candy instead of doing your homework, for the most part, it probably shouldn't affect your grade. Okay? So we probably have some kind of scatter plot that looks like this. Okay? I mean, one person might eat 20 pieces of candy per day and still get this grade. Another person might only eat 2 pieces of candy per day and still get the same grade. Okay? So we probably have some kind of scatter plot like this. Okay, so there should be no linear relationship. At least we would hope. I try not to grade you based on the amount of candy you eat. So now let me ask you, if you were to draw a line of best fit through this data set, what would that line look like? Probably something close to horizontal. Okay, and if it's perfectly no relationship whatsoever, that will be an exactly horizontal line. Okay, so if you have no linear relationship, then your slope is going to equal 0. So I don't know if you remember on one of the first pages, we said as long as you have a non-zero slope, then your variables are linearly related. Okay, so if I'm going to ask you a question, so it seems like it might make sense to try and do a test to see if our variables have a linear relationship. And if we want to do that test to see if they have a linear relationship, I'm basically going to be asking you, is the slope 0 or something besides 0. So here's our t-test for slope. Okay. We're going to use this test, okay, if we want to know the value of the population slope, beta 1. Okay. Or if we want to know if there's a linear relationship between two variables. So anytime you want to know is there a linear relationship or you want to know what your slope is, you can come use this t-test for the slope. Now there are some assumptions to use this test. Okay. They're not assumptions that we're checking here, but again, if you want to take that 5100 class for linear regression, you would spend a lot of time on this. Okay. The assumptions are that the errors are independent, that they are normally distributed, and that they have constant variance. Those are assumptions. Okay, the null hypothesis, status quo, okay. Remember we said our null hypothesis is always going to be an equals value for me to go through and find the p-values. So our null hypothesis is that our population slope is equal to 0, which would mean that there is no linear relationship. Okay. And if I find a lot of evidence against that, then I can say there is our linear relationship. Our test statistic is, okay, but remember, what's our form for test statistics? It should be estimate minus hypothesized value over the standard error or standard deviation of your estimate. Okay, so that's what the form we use for everything so far. So in our case, our estimate for our population slope is beta 1 hat. What's my hypothesized value of my slope? It is 0, and divided by the standard error of our estimate, which we write standard error of our slope. Notice, because we're just minusing 0, we can simplify it to this equation, which again I used the notation from another class. I'll have to go fix that. But it's beta 1 hat over the standard error of beta 1 hat. Also notice here that we still have n minus 2 degrees of freedom. So, just like we usually do, we have 3 different alternative hypotheses that we can look at. The first one would be that our slope is greater than 0. If you have a slope greater than 0, then you can say that you have a positive linear relationship. Okay? And we would be looking for the area in the right tail. If your slope is less than 0, then you could say that you have a negative linear relationship and look for areas in the left tail. And finally, if you don't know whether you thought that the line should be going up or down, you just want to know if there is some kind of relationship, then you just test for not equal to 0, but all you could say at the end is just that there is a linear relationship. You couldn't tell me whether the line is going up or down. And you'll be looking for the area in both tails. Now just to note that Megastat on its output only does a 2-sided hypothesis. So if you want to test specifically for a positive or negative linear relationship, you have to find the p-value by hand, which is one reason why we still learn how to do it by hand even when we have computers. So our same study, we want to see if non-exercise activity could help reduce fat gain. So here are the results. And we're also going to use this as a review for everything we've already done. Okay. So predict the mean fat gain for an NEA level of 101. Okay, so again, this is just a review. What would you do at this point? Let's see, let's write down our equation of our line first. So y hat is negative 0.0034x plus 3.5051. Okay, and if we want to predict it, so the mean fat gain for everyone that has an NEA level of 101, I would just have to plug 101 into my equation. So it looks like if you only have an NEA of 101, you're still going to be getting 3.16 units of fat. Predict the fat gain for a single person with an NEA of 101. Okay? And so we said that there's no difference between whether you're trying to predict the average or predict it for one person. I would still just have to plug in 101 into my equation. So it's still going to be 3.1617. I might ask you something like, what is your correlation? And what does it mean to us? Okay. So can you find your correlation on the output? Okay. Our symbol for correlation is R, so R is negative 0.779. Okay. And as far as what does that mean to us, basically I'm asking you to check for two things. Is that a positive or negative? Negative. So we know that we have a negative linear relationship. Okay. And how close is that? Is that closer to 0 or to 1? Or negative 1, I guess. Okay. So a correlation of negative 0.779, that's closer to the negative 1 than it is to the 0. So we can say that it should be fairly strong, we think. Okay. So just based on the correlation, because my correlation is negative 0.779, I think that it's going to be a negative linear relationship and probably fairly strong. So that's what you can tell from your correlation. Now, we always prefer, though, to not just look at things like our sample mean or just our correlation, or even just to look at my slope, which is only negative 0.0034. We prefer to actually do a hypothesis test and let our numbers tell us whether that was statistically significant or not. So let's conduct a hypothesis test to determine if there is a linear relationship between NEA and fat gain. So just follow the normal steps of testing, like picking your significance level, which is the 0.05. Picking your null and alternative hypotheses. So the null hypothesis is always going to be that beta 1 equals 0, so no linear relationship. And what is the alternative hypothesis in this situation for this problem? Okay, so you're thinking we should do less than 0 because my slope was negative, so that's what you're already suspecting. However, if you look at the problem, I just said test to see if there is a linear relationship, and I didn't tell you whether I suspect that it's positive or negative. So in this situation, let's go ahead and do a two-sided, because it only just asked if it's a linear relationship, didn't ask whether it's positive or negative. Okay, so this would be just that there is a linear relationship. Okay. And really that slope that we had is pretty close to 0, so it might be good to do this test to see whether or not that's actually significant. So we have our alpha, we have our hypotheses, we're going to skip assumptions for this class, for this test. So we can go on to our test statistic. So t equals the estimate for our slope over the standard error for our estimate. So come back up to look at your output. Our estimate for our slope is negative 0.0034. And our standard error for that estimate is 0.0007. Which puts me at negative 4.857. So even though that slope is really small, my standard error was also really small. So my test statistic is actually pretty far out there in the tail, I think. But we want to figure out exactly how far it is out there in the tails. So I need degrees of freedom, which are n minus 2. Looking up at the output, n is 16. And my p-value, I want the area in both tails. So come to the t-table, 14 degrees of freedom, I'm looking for 4.857, which would put me out here. So something smaller than 0.0005. So that tail is less than 0.0005. This tail is less than 0.0005. So my p-value is less than what? 0.001. Because I have to double it since I have two tails. So is that a big or small p-value? Small p-value. Reject the null hypothesis, which means that we have, this is less than 0.01, that's extremely strong. Evidence that what? My slope is not equal to 0, or that I have a linear relationship. So we have extremely strong evidence that there is a linear relationship. Which makes sense. I mean, we looked at our correlation, and our correlation was high enough that we thought that there was probably a fairly strong linear relationship. And we did our test, and our test shows us that our slope is definitely not 0. It doesn't tell us what our slope is, but definitely not 0. So we have very strong evidence that there's a linear relationship. Okay. Now I just want to point out a couple things. Okay. Notice again, it does tell you degree of freedom on the output, and it also tells you your test statistic. Notice we got negative 4.8, they got negative 4.6. Why do you think that is? Okay. It is actually exactly the same, but because we're dividing by such a small number, 0.007, they rounded that just a little bit. If we go into the actual output and expand the number in Excel and divide the two numbers, then we'll get the exact same thing. So we're only just rounding, but it's quite a big rounding difference because we're dividing by such a really small number. Okay, so it will tell you the exact test statistic, and it will tell you the exact p-value. Notice the p-value is less than what we got of 0.0001. Okay, so entire column, any questions on how we do that? So, 9 minutes, we should probably be able to finish this next problem, just kind of a review for everything that we've done so far. So a study looked at the number of thousands of steps per day, called PA, and the body mass index, BMI. Okay. Now in this situation, what do you think might be the variable we're trying to predict? Okay, we probably want to predict body mass index, which means that our explanatory variable is number of steps per day. I think PA is short for physical activity. Okay. Notice in the megasta output they did put the dependent variable, the one you want to predict, is BMI, and the explanatory variable as the PA. And so our second line there will be our slope. Our equation for our linear regression line, I just have to pull off the output. So y hat equals, let's see, my intercept is 29.5782 minus my slope of 0.6547 times x. So looking at the output, what is my correlation? Our correlation symbol is negative 0.385. And what does that mean for us? If it's negative, that means we have a negative linear association. We have a negative slope. And negative 0.38, how strong of an association do we have between these two variables? Kind of a so-so strength. What is your estimate for beta naught? Beta naught is our intercept. And our estimate for our intercept is 29.5782. And how would you interpret that? What does it mean to us?
If you don't walk at all,
so if you don't walk at all, so if you have 0 steps per day, your expected body mass index is 29.5782. Okay, could that be a practical interpretation? If you don't walk at all, could 29 be a realistic BMI? Probably, so this one could have a practical interpretation. Now, what is your estimate for beta 1? And interpret that. That will be our slope. So beta 1 hat is negative 0.6547. So what does this mean for us? So for every additional, what was our unit if you look back up at the problem? So for every additional, I think it's thousands of steps. So for every additional 1,000 steps, we expect the BMI to decrease by 0.6547. So for our next one, let's find a 99% confidence interval for our slope. So again, this is the reason you might want to be able to do it by hand, in case you want 99%, which is on your computer output. And we'll also interpret while we're at it. So let's draw our picture. We want 0.99 in the middle. How much is left on each side? 0.005. We also need degrees of freedom, n minus 2. So let's go back up and look at what n is. N is 100. We looked at 100 people. So this is 100 minus 2, which is 98. Okay. What are we going to have to round to use our t-table with 98 degrees of freedom? And we're going to run all the way down to 60. Okay, so 60 we wanted 0.005 in the middle. So it looks like we're at 0.266. Yes, 2.66, thank you. So t star equals 2.66. So our formula, remember, is our estimate for our slope plus or minus our critical value times the standard error for our slope. So, look back up at your computer output once again. Our slope is negative 0.6547. And our standard error is 0.1583. So let's see, so 0.6547, actually negative 0.6547, plus or minus our critical value, times the standard error. So negative 0.17 to negative 0.23. And what did you tell your boss that that means? Something like, we are 95% confident that if we increase by 1,000 steps per day, your BMI will decrease between negative 1.07 and negative 0.23 units. So, any questions on this? It is 9:30, but I will just record the last of the problems part here.
You'll be in your office later, right?
Yes.
Okay, cool.
So this is our hypothesis test. We want to see if there's a negative linear relationship this time. So pick your alpha, 0.05, and we need our null and alternative hypotheses. So we want to see if there's a negative linear relationship. Well, I guess our null hypothesis is that there's 0, so no linear relationship. And our alternative hypothesis, because we want to see if there's a negative linear relationship, we're going to do a less than. Our next step is always our test statistic. In our case, it's our estimate over the standard error of our estimate. So looking up above, our estimate is our negative 0.6547 over the standard error, which is 0.1583. This gives me negative 4.135. So we're at negative 0.4135. We're looking for the area to the left. Once again, we need degrees of freedom, which is n minus 2, and n was 100, minus 2, which gives me 98. So looking at our t-table, once again we have to round down to 60 degrees of freedom, and we're looking for 4 point something, which puts me up over here off the chart, so my p-value is less than 0.0005. Now this is a small p-value, so we need to reject the null hypothesis, which means that we have extremely strong evidence that there is a negative linear relationship.
She said only 3 out of those 5 are going to be included.
So, negative linear relationship. Now, just as a note, the very small p-value just indicates that we're very sure that there's a linear relationship between the two variables. It doesn't tell us how strong the linear relationship is. It won't actually tell you what your slope is, or necessarily like what your correlation is, or how strong your relationship is either. Just that we're very sure there is a negative linear relationship.